Hello and welcome, everyone. Welcome and happy New Year if it's not too late to say. Welcome to because it's our first alumni event of 2025. But we will go to continue something we started in 2024, our celebrations of 50 years of co-education in college. So far, we have had the event for Meeting Minds, where we met with our colleagues at the other four colleges. We had our gala night in the Digital Hub, where we were rocking the hub, I think is the best way of putting it. And then we had the reimagination of Love's Labour's Lost into 1974. So now we continue into something else, which we a new initiatives since we celebrated 45 years of co-ed, which is of course Zoom, which was barely something that anyone would have known about in 2019, but of course we all very much now know about. And it meant that we can connect with people throughout the world. So we thought, what better than have two international speakers to be part of this celebration? So it is my absolute pleasure to welcome Drs. Nancy Levenson and Sarah Rugheimer to the call to discuss women in space science. And I'm going to actually let them do their introductions as part of their conversation through the topic. But just one small request from our speakers. Usually we'd ask you to turn all cameras and mics off. Now, we would still very much like you to turn mics off, but feel free. This talk might contain references to black holes, but the one thing we didn't want was the Zoom black hole. So we are happy, they're very happy to see your smiling faces during the talk. So without further ado, I should say as well, if you have any questions for our speakers, feel free to drop them in the chat box and we will have time at the end to ask our speakers the questions. But as I say, without further ado, Sarah and Nancy, over to you.
All right. Sure, I'll kick it off. I'm Nancy Levenson. I'm from the United States. I grew up in Arizona. I had originally studied astronomy and astrophysics at university, and that was at Harvard. And then I had the opportunity to go to Oxford and Jesus College specifically to read physics and philosophy. So for me, that was an exciting change, something different. At that point, though, I also learned very much that I depend on data to motivate me, not just theoretical ideas. And so following Oxford, I completed a PhD in astronomy back in the US at the University of California, Berkeley. And I had continued a pretty standard academic path after that with some postdoctoral research and time as a faculty member at the University of Kentucky before I made a big switch into astronomy administration and leadership. And so I've been working at large space organizations since then. And so first I was in Chile with a ground-based international observatory, the Gemini Observatory, where we operated telescopes in Chile and Hawaii for an international consortium. And now I'm at the Space Telescope Science Institute in Baltimore, Maryland, where we are the Science Operations Center for the Hubble Space Telescope, the James Webb Space Telescope, and we're looking forward to the Nancy Grace Roman Space Telescope. And I still do a bit of research, and we'll talk about this, I'm sure, more later, on galaxies that not only have supermassive black holes in them, but those black holes are actively feeding and they're taking on material. And so there are effects that we can measure as a result of that. I'll turn it over to Sarah.
Yeah, thank you guys so much for coming. My name is Sarah Rugheimer, and I am also from the US originally. I grew up in Montana. And I first went to a community college, Flathead Valley Community College, for a year before doing the rest of my undergraduate degree at University of Calgary. And then I went to Harvard for my master's and PhD. After Harvard, I went to University of St. Andrews in Scotland, followed by a 4-year fellowship at Oxford Jesus College. So that's also my connection to Jesus. And then I took a faculty position at York University in Toronto. That's where I currently am. And yeah, similar, this is a very typical academic path. You have to move a lot. You move internationally a lot often. And, when I was 19, I couldn't imagine that I would have 3 citizenships, but indeed now I do. I am now a British and a Swiss citizen, along with being American. And part of this astronomy career is I have been able to travel the world and live in a number of countries. So that's been really exciting.
Thanks so much. So I think to begin with, do you want to talk about how a bit about your research and how working in STEM has been for you, and particularly in terms of the topic, obviously the theme of this event, how being a woman in STEM has maybe changed since you started and continues to develop. Are there still the glass ceilings that are still there, and but also how much progress has been made?
Yeah, Sarah, do you want to start with that one?
Sure. Yeah, so let's see, when I started my undergrad, it was 2002. There has been a lot of changes. I'll say there's a big difference between astronomy and even physics, even though most of us have a physics degree as our sort of primary degree. Astronomy has a lot more gender parity than other sciences. So kind of in order, I think it's biology has the most number of women in the field, less women in chemistry, less women in physics, less women in math, but astronomy is actually 30% women PhDs. And now we're hiring at about 30% new faculty women. So that it has been quite a change over the last few decades where we're seeing hiring rates match our rate of PhDs. Of course, there's still misconceptions, preconceptions people have. I've definitely overheard comments which are discriminatory towards women in science, either directly myself or, when someone doesn't think I'm listening and a comment's made. So it's not that those don't exist. I do think we've made a lot of progress. And, that's kind of one, I think, amazing thing about astronomy and planetary science is it is more gender diverse than other fields.
Yeah, to add to some of that, I think also these communities of astronomy and planetary science, I think there's genuine attention across the community, and it's not just from the women or other underrepresented people, but a real recognition that we want to take advantage of all of the brains and the skills that are out there, and that means being inclusive. So through some of our professional societies and other kinds of work, there's real attention to that. It's great that now there is that match in the flow from PhD success into faculty positions. There has historically been a lag as you go up in seniority, that the lecturer, assistant professor level lag behind the senior full professor sort of level, and so there's still some of those residual effects. Although it's definitely changed over time. For me, even I would say over the last 5 years, it's become noticeably different that I am much more rarely the only woman in the room in some kinds of conversations, and so I think that's progress, and so it gets to the point where it becomes less of an issue. I will say, Sarah had mentioned that that there are still some biases that are out there. One of the things that we do at Space Telescope is we run the peer review to get time to be able to use Hubble and Webb. And one of the innovations has been going to a dual anonymous system where not only do the proposers not know who's reviewing them, but the reviewers don't know who the proposers are. And we have a lot of history with Hubble to be able to see. With Webb, it's always been this way. And it really was with the introduction of this dual anonymous system that we finally are reaching real gender parity. That it was a small but persistent effect previously, only in one direction of more men leading the effort, and now that there's less attention to the scientists, and then that opens opportunity for all different kinds of people. We find many more students and early career folks also get opportunities that way when we focus on what's the science question and not on the people.
Absolutely. And I was just wondering, picking up on Sarah's point as well, about working internationally. Is there a particular difference you notice maybe in work in the UK versus US, or indeed around the world? Are these advancements of internationally recognized, or are there some countries ahead of us or behind, or well, I say us, UK, but obviously US as well. Do you notice any differences when you, let's say, do conferences in other parts of the world?
You mean in gender or just in science, or
In
like what?
gender and science, or indeed any of the questions raised.
Mm.
Yeah, I've noticed a difference. Certainly there are different what's culturally acceptable to say is different, and some countries are more direct. And so I've heard some more, I would say, discriminatory remarks in some countries which have a reputation for being very direct, which is interesting. That not necessarily in the UK, which has the the opposite reputation of being very indirect. And so, there is, of course, differences around the world, but astronomy is very international. So it's I think slowly but surely we're seeing those sorts of things, be more parity around the world. I'll say in my physics department here at York University in Toronto, we have 28% women as faculty in our department, which for a physics department, it's not even an astronomy department, is quite rare,
Yeah.
we think we're doing very good, so, definitely that was not the case when I was an undergrad. There was one woman faculty, and typically, as I was going through the ranks, there was typically only one professor in a department where I was visiting.
Yeah, and I'll comment a little on the other just sort of general international aspects. I mean, that's one of the things that I have absolutely loved about this field, that my strongest collaborations, the people that I work with consistently, are from all over the world. And now with modern technology, we have some really good ways to do that and to be able to keep up with each other and the developments that we're making. And so I think that is just a great part of it, is that we all collectively pay attention to the results that are coming out from around the world. The biggest challenge is just the fire hose of information coming at it, keeping up with all of it. But it's not really segregated by country, and so there are important developments in lots of different places. And that also makes me think of another aspect of this, is that a lot of these major activities in this kind of field are such a great opportunity for international collaboration at the truly national level, and so I think that's really great to have those opportunities, and to realize that there can be different strengths around the world. And also, as astronomers and planetary scientists, our ambitions are much greater than often any single government is willing to support. And when we gather together, then we're able to make things happen.
Yeah, you were saying when we chatted last week about this, that the idea of government support and how it's sort of like cross-party. I don't know what either you want to discuss about how government support helps maybe your work, or can maybe hinder some of your work. I don't know, in terms of what, and particularly maybe of working in different countries, and how that greater funding can change what possibilities that there are for you. I don't, who might want to pick up on that one?
Sure, I can start in on that one, and that's something that at least historically, support for this kind of work has been nonpartisan. That people of all different political frameworks tend to see the value in what we do, and so at least historically, there haven't been big swings of worrying about who's in government to decide whether or not we're able to continue with these activities. So that's generally how it's been going. I will say we absolutely depend on government and public funding for what we do. Again, this is the scale of what we need. It's that the light is so limited. We're looking at these faint things that are very far away, and so there's just a limit to what you can do with small things that any one university might be able to support for its faculty. And so then these do become public issues, and so we really do count on that. And so I still believe, as you all are probably aware, the United States, we're trying to understand what are our changes that we're going through right now. And right now there is a bit of upheaval even for us, that space science isn't isolated. And so I am looking forward to it settling down, and remain optimistic that we'll be able to continue on course.
Yeah, and I think just also it's interesting when you look around the world how kind of varied the funding landscape is. So for example, here in Canada, the grants are much smaller, way smaller than in the UK or in the US. A typical, starting grant for new faculty is maybe 25,000 Canadian a year, which wouldn't even buy paper clips, in a lot of funding areas. But in Canada, students are highly subsidized. So with that 25,000, you can support 2 PhD students, for example. And the grant success rate is 60 to 80%, which is like unheard of, in other like parts of the US. It may be sub 10%, 5 to 10%, same in the UK, same in Europe, where the grants in the US and Europe maybe are $1 million, for like, some sort of large grant that you get to fund a team from NASA, and that comes with a lot of overhead and whatnot for operating the university, which Canadian grants don't. So the funding is definitely very different in different countries, and we do sometimes see political tensions. I have a graduate student who is Chinese, and that has unfortunately limited some of the collaborations that she may be able to take because of government policies on Chinese nationals working with scientists. So then, that's something I've just kind of seen throughout my career, that, there are these different, there are government rules and regulations in Europe, in the UK, as well as the US, and just a very different funding landscape. The US does fund space science a lot more than other countries. Typically, the US budget for NASA is 0.4% of the budget, 0.4 to 0.5%. So like half a penny on the dollar. In other countries, it's typically 10 times less, around 0.05 or something like that. So, and then that intrinsically means a lot of the big missions are heavily NASA dominated. So the James Webb Space Telescope is, it was an $11 billion mission. 10 billion came from the States, and roughly 1 billion was from Europe and Canada. So like the dollar per person per country, the US did pay more. It's like, I can't remember what it is, like $26 per person, whereas in Canada it's like $3 a person for the James Webb telescope. And but that said, these large telescopes always need international collaboration. Not always, like not all of the expertise exists even in, say, the US. You need Europe is really great at like infrared detectors, and there's just different strengths in each country's industry, and so you see a large scale cooperation for most of these missions.
Fantastic. And I think that mention of the James Webb Telescope leads naturally on to basically now addressing both your work. So Nancy has this simple question: what are you working on at the moment? Tell what is the latest with the telescopes?
Sure. I'll start with some of immediately what I study. So as I said, galaxies with the supermassive black holes in them, and they're actively feeding. And this feeding is part of a whole process, a cycle of, there is both feeding and outflow, and that affects the formation of stars in these galaxies. And we see in a few different ways over cosmic time, and in individual galaxies, there are intrinsic relationships between the black holes, how massive those black holes are, and the stars that exist in the galaxies. And so those are the kinds of questions I'm ultimately trying to get at. And I happen to be particularly interested in, so that this activity, the feeding, releases a lot of energy that we generally see in the form of light. But sometimes that can be hidden, or blocked by dust, by gas, and I actually pay a lot of attention to the distribution of that material right around the center of the galaxy. And so Webb has been so helpful for my research because that dust turns out to emit light at wavelengths longer than what our own eyes can see, so infrared wavelengths. And so some of the capabilities there are just terrific to get this fine detail on where is the dust, how is it moving, how is it related to the gas that's in the galaxy. Those are some of the details that I tend to get into, chipping away at this really big problem of stars and black holes and galaxies.
And my research is on exoplanets. These are planets that orbit distant stars and how we get to detect signs of life in them. So our own biosphere on Earth leaves a large imprint of molecules in our atmosphere that indicate that we have life, like a whole biosphere of life. And so what I'm mostly interested in is how could we detect those on other planets? You know, they're far away, the signal to noise is hard, and we can't like go and take a picture of said life. So it's always teasing out from a noisy spectrum, which is where all the interpretation and the debate and the controversy tends to be. So it's not easy. And James Webb is the very first telescope in human history that might be able to make a biosignature detection. But it's at the limits of what James Webb can do, really at the limits. And James Webb is expected to only get the spectra of maybe a handful of rocky habitable planets. So if it does find something interesting, I'm sure we're going to be arguing about it for decades until we get the next generation of telescopes. So my work largely doesn't focus on James Webb. It focuses on building that next generation of telescopes, which will be able to observe dozens of habitable rocky planets and get the spectra of enough planets that we can start to statistically answer this question. And even if we see nothing, we would have observed enough that would be interesting to kind of rule out how common life, Earth-like life, is in the universe. I also I do a lot of public outreach, and I'm writing a course on the James Webb Telescope and all of its cool things, and that's being done through the Great Courses and will be out sometime later this year.
Fantastic.
And
Oh, sorry,
I
Nancy.
just wanted to add that what Sarah is trying to do is really hard. It's a 1 in 10 million problem is the kind of level that we're doing with Webb. That, you know, for every 1 photon of light you get from the planet you care about, you're swamped by 10 million from the star. And it just points out that trying to detect those atmospheres of Earth-like planets around sun-like stars is a 1 in 10 billion problem, and so that's why really some of those new facilities will be necessary.
Yeah,
I mean, what just struck me when you both discussing your work is, I mean, and I at this point will confess I was very much on the arts side, so I'm very much non-specialist asking this question. But I think those of us who aren't in this area hear words like black hole and life on other planets, and immediately there's a popular there are terms in popular culture. I suppose I just wonder if either both of you on those two areas want to stress how should I say with the popular sci-fi version, let's put it that way, how does it differ? What are the main things that if you could just tell a member of the public, no, it's not like that? What particular areas would you pick up on? I don't. Sarah, do you want to go first?
I mean, aliens has so many misconceptions, right? Like when I say, you know, I'm interested in how we could detect alien life or microbial life on other planets. I mean, first off, people think we're finding like Pandora, you know, tall people with blue tails and bioluminescent vegetation, and, you know, that it's going to be really easy. And, you know, indeed, we do these things not because they're easy, but because we thought they were easy. And now we realize that they're still, they're near impossible, but they're interesting enough to try. And so I think the biggest misconception is that we've already found life. That's probably the number one thing that I come across is people think that we've already announced it, because there's been some very poorly worded press releases where people have said we found this planet that 100% probably has life on it. I've seen that written in the news, and I've also, with all the interest in UFOs, or now as they've been rebranded UAPs, people just think that we found life or that we're hiding life. So I've had my own sister was it around the Mayan apocalypse, and was it 2012? She like called me and she was like, Sarah, you would tell me, right? So, she was like, you would tell me. And then, and she's like, I know you couldn't tell me though. I think that, yeah, she also said that. She was like, because you wouldn't want to cause mass panic, but you would tell me. And so even, it's just really these misconceptions of astronomers hiding science. And if you knew astronomers, you knew we wouldn't be able to. Like, we're very independent, want to be the first to a discovery and get all the glory sort of person often. And so like someone would squeal, I'm just telling you, someone would squeal. There are no aliens. I wish there were aliens. And if I knew that there were aliens, I would definitely say something. But we have not found robust evidence of alien life. So I think that's the most common misconception I get. What I'm doing in my day-to-day is computer modeling, finding errors in my Fortran 77 code, plotting squiggly lines. It's not as exciting as the movies make it out to be, but of course the concepts are wonderful.
Let's see, and then on the black hole sides, it sort of goes in two different directions. And one misconception is, whether they even really exist, and we really do have very good evidence for these things that are extremely compact and massive for their size. We see them on lots of different scales. There's a supermassive one in the center of our own galaxy. There are less massive ones all around. So they really do exist. And then a piece then that follows from that is then do we need to be afraid of them? Right? If there's a black hole at the center of the galaxy, isn't it going to swallow us all up? Isn't that going to be a problem? And the answer to that is no. It can be a problem when you're super close. Yes, you can't avoid it. Actually, the same way that if you get super close to a planet, you can't avoid it. You'll hit it. You'll run into it. So there's that aspect. There are other aspects out there in the public conception that some of it is really a matter of we are at some of the limits of our current physics, and the physics within black holes is different from the physics that we can approach and experiment and really get a handle on outside of them. And so there are lots of descriptions of strange effects that probably occur there. And some of those really weird things, though, may be our best scientific descriptions of what's going on in those extreme environments.
Fantastic. Thank you. Because I think do you think, just thinking about it, the idea of that connection, obviously we talked about the idea of we can communicate with so many people now and with the public as well. Do you think that sort of the pros and cons, I suppose, of that social media generation? So the idea of, how do you harness that to be able to spread, just say, the truth, as opposed to also dealing with, and I suppose going back to some of our comments before, when people do have the idea, are you hiding things from us? Twitter is not, well, sorry, X as we now must call it, is maybe not the healthiest place for that. So how do you both judge that and, I suppose, juggle those dual concerns of trying to educate, but also dealing with people who, quite frankly, will not be educated?
Yeah, I think that's a real challenge. I think overall, the easy thing to say is I absolutely fall on the side of wanting to communicate. Some of it goes back to this very fact of this is a public endeavor that we are part of, that this only happens because of the support that we get from people around the world. And this is a part of giving back and letting you know this is what we're doing. This is what we're doing since you've invested in it. So that part of it is absolutely important. And there's the reality that social media, that is the type of media that people use, and that's a shift, right? We used to be able to rely on formal press releases that went to the big newspapers and maybe occasionally a national TV broadcast. And that was solid information down, top down. And now that's not what people are turning to. And so if we want to communicate, then engaging where they are is important. And I admit, though, I don't quite have an answer to that fact that with lots of conversation, sometimes it goes astray, and it's hard to bring it back and ground it in the facts as we know it. And then an added complication with all of it is the general process of science is we're discovering and changing. It's not a fixed set of facts just to put out there once and have everybody learn and then we're done. And so there will be change. There will be change over time. And what we said a couple of years ago about some things is wrong, and we're revising that. And so there so there's that aspect of it too. So I don't have a good answer. Maybe Sarah has a better approach that we can be taking to engage.
Yeah, I mean, it is something I spend a lot of time thinking about as someone who does do a lot of outreach. It's very hard, because you want to convey, as Nancy was saying, the process of science, which is that we're constantly having theories, testing them, revising theories. But that doesn't mean that everything is wrong and everything is up to change. So this is like the other hard part of that, is that realizing that, sure, even though Newton's laws are incomplete and that relativity is needed, it doesn't mean that when you're throwing a baseball, you can't use Newton's laws. You can use Newton's laws. Newton's laws just don't work, at very fast speeds or around very massive objects. So they're not wrong. So this idea of wrong is, I think, incorrect, actually. And then that misperception in the public when they see, a theory that is kind of encompassing new data and it's changing, but it's changing in a way that doesn't usually get rid of everything that came before it. So that sort of nuance in the scientific process, I think, is really important to communicate, because unfortunately that distrust in scientists has real world consequences. And I often bring up, I had a friend who, didn't believe in medical science and died of a cancer that was quite easy to treat, a cancer with a very high success rate for permanent remission. So this sort of inability to understand, like, where is our knowledge incomplete, and when we say something like this is the best knowledge we have, and maybe we saw this in the pandemic, maybe we're getting new information and that's going to be changing in a couple months because we are in a period of rapidly changing information. How to communicate that is exceptionally hard. And so typically one thing that I really enjoy thinking about is communicating science at multiple levels, so that you give your one sentence overview, but then they can see the paragraph summary, the detailed page summary. They know that they're only getting a small slice of it, and they know where to get the more advanced knowledge and to see where their own understanding trails off. So there's some great examples of this, particularly in climate change communication. And on YouTube, there's this whole series of videos called by Wired, called Explained at 5 Levels. And it's a scientist giving an explanation of their research to a 5-year-old, then to like a 12-year-old, and then to a college student, and then to a graduate student in the field, and then to a fellow expert. And you can see how the little one sentence, short paragraph summary is not the whole story. And if you only know that, you don't understand the whole thing. And so that, I hope, brings in some humility when we're reading press releases, and to realize that there's a lot of nuance in a lot of these things.
Fantastic. And I can see we already have questions starting to come into the chat. So I'm just going to ask one final one. Yes, if anyone else has questions, please do enter them in the chat and we will come to them immediately afterwards. But what I just thought we'd end on to get us back to the first topic. I think we might potentially have some students on the call. And if not, we're definitely going to share the recording afterwards with them. What would you say to either, say, one of our female undergraduates reading science, or indeed, let's say a female sixth form interested in applying to it? What would you say to them as why should this be an area that they should be, because you're both incredibly passionate about it, what would you say to them?
Nancy,
I
do
don't
you
Okay, sure. I'll take that one first. So my the thing that I think about for anyone is it is important to find where your own passion is, and so I can speak to some of the things that I love about science and my approach, and then if that speaks to somebody, then it's relevant. I love this opportunity for discovery that I can identify some particular aspect of the universe that we don't fully understand, and by following through on it, I can make some discoveries. I can advance our knowledge about the universe, and that's just fascinating. I actually like the open-ended nature of it, that it's not repetitive. It's not a fixed body of things to return to, and so if those are ways of working and ways of thinking that are interesting, then those are absolutely worth doing. And then I do also think even more broadly about the range of skills and the different expertise that we need to make all of these things happen. And so there's also room for people to contribute in different ways. Web is a great example that we've estimated something like 20,000 people around the world made some contribution to it. They're not all astronomers. The vast majority of them were doing other kinds of work, incredible amount of engineering, materials, optics. So huge range of technical and mathematical skills, as well as the more pure astrophysics that we're trying to do in the end. And so I think thinking about that whole range of things is that you might love the subject and have multiple avenues to be able to contribute to it.
Yeah, and also just to say, like, diving into a science degree of any sort gives you a wide range of skills. And we know that not everyone is going to want to stay in the academic path or, within astronomy, or, there's so many different paths one can take. And I think one thing that came out of a US jobs report maybe 10 years ago was that the unemployment rate for astronomy PhDs was like 0%. It's one, very few fields have a 0% unemployment, but people find jobs somewhere. It's maybe not astronomy. They might be going into finance, into industry, into all sorts of different areas. Data science is a big pipeline for astronomers. You could be working in all sorts of different avenues with that skill set. So I think it's really important for students to know sort of how to market themselves to different areas and how to be able to pitch their skill set when they're in a job interview, and also to just do informational interviews with people outside of astronomy or planetary science to have kind of a perspective open of what sorts of jobs they can do. Because the reality is we're 4 times oversubscribed in terms of PhDs to jobs directly in astronomy. So that does mean a lot of people are going to be finding jobs outside of astronomy. And I still think it's great that they're getting a PhD in astronomy or planetary sciences, because it gives you a lot of tools for many different careers. So I think that's the main thing I would tell students, is to not like kind of put all your eggs in one basket. As a student, get those, go to those career panels and networking events and whatnot to try to look at what else you might really be excited about. So that's kind of like just my one piece of advice there.
Brilliant, fantastic. Well, we do have quite a few questions now, so I will go through. So the first one is a question about I'm not sure if the 2 US men and female astronauts are still stuck on the International Space Station. If so, any comment on their prospects for international transport for return journey and how to cope from day to day? Apparently, the international crew had no jobs to delegate to them.
Yeah, it's actually something I've talked a lot about in the media here in Canada. I get asked like periodically to go on TV and radio for this one. Suni Williams and Butch Wilmore have been stranded in space. You know, they went up on the Boeing Starliner for, you know, in last summer for what was expected to be 8 days and have not returned. Now, let's just dispel one myth. They're not stranded. If like an emergency were to happen, they could get back, right? It's just that given the cost and kind of timescales of missions, you don't send someone back just because they want to go, or you know, or like they have, you know, a I don't know, like a birthday party to host, right? So like you have to put them into the regular schedule of getting them down safely. So they're coming back. You know, it's soon. They'll be back probably on the SpaceX Dragon capsule coming back on just a regular scheduled return. And they are doing jobs. They are doing research. They're doing work. They were just on a spacewalk recently, but you know, there's always things to do in space. They're not just twiddling their thumbs. They are active astronauts. They've been doing this their whole life. They were part of a test mission. They knew this was a possibility. Suni has been in space a lot, and you know, they are very qualified, capable astronauts that are certainly out there doing lots of cool things.
Fantastic. Nancy, do you want to add anything to that, or should I?
No, that was a more complete answer than I would have been able to give, so nothing to add.
Well, I'll take next. Actually, Malcolm has 2 questions, so I'll take Malcolm's first one first. Given the new objects being found and the distances involved, does a single Big Bang still make sense?
So this is a great example of some of what Sarah was talking about, is that even as we're making these new discoveries, we're not completely throwing away what the foundations that we already had. And so the overall concept of a Big Bang, where this was the beginning of time and space for our universe, that still holds. There's nothing that we've found that suggests otherwise. One of the things, though, is that the kinds of measurements that we're making now are mostly getting at some of the first galaxies to exist in the universe. And so we as astronomers think of these as incredibly early galaxies, only 300 million years after the Big Bang. And so there's still that some of the fundamentals of those first instance we're not really probing with these kinds of measurements that we're getting much later. I mean, so far everything is consistent, but we're not really doing deeper probes of some of that right now. So currently that aspect of what we think we know about the universe still holds.
Fantastic. Sarah, do you want to, or should I move on to Malcolm's second question? So, what type of advances? Actually, you mentioned this because of the new telescopes. What type of advances are people looking for in post James Webb telescopes?
So I'll speak from the life detection perspective. As I mentioned, James Webb is just not designed for rocky Earth-like planets. You know, it's doing a great job for bigger planets, Jupiter size, mini Neptunes, Neptune size objects. Just need more resolution and bigger baseline and a larger, you know, more collecting area, more photons. We need a bigger telescope. And so there are 2 main efforts. There's some from the ground too. I'll briefly mention 3 types of telescopes. So one is the Hubble Worlds Observatory, which is NASA's next selected large-scale mission. This will be a kind of the mega Hubble, you know, in say launching in 2045. I don't know, you know, it's going to be at the
but you're right. You might have to be realistic with that.
You know, I hope I'm alive. Anyway, so we will launch that telescope, and that will be able to observe many, just with its collecting area. We're really, what am I trying to say? We're in a problem of not getting enough photons, which means that we just need a bigger bucket, a bigger light bucket to get more photons, because these planets are hard to see. They're super far away, and so we just need a bigger telescope. And so the Habitable Worlds Observatory will be one, as well as in Europe, there's a mission concept called the LIFE mission, the Large Interferometer for Exoplanets. And I'm part of that mission team. And that one, I think, has a better chance of actually detecting biosignatures because it's in the infrareds, similar to James Webb, but bigger. And that's where most of the molecules absorb and have features. We also have really cool telescopes coming online on the ground. So the extremely large telescope, the ELT, will be able to do biosignatures in Earth-like planets from the ground. It's a 39-meter telescope in Chile. So those are sorts of, it's basically bigger, better telescopes. You know, if I could have a telescope, you know, the whole size of the moon or something, I would love that. But, you know, that's not feasible with technology and current budgets.
Yeah, so Sarah absolutely got some of the key major things that astronomers and space scientists are looking forward to. Just to add a little bit more to that, so going bigger is really helpful, and then we get these different kinds of capabilities as we think about what's on the ground and what might be in space. One of the advantages of space is that that's where we can detect ultraviolet light. Happily for humans, our atmosphere protects us, so the ultraviolet light doesn't get down to our ground-based telescopes. But that's really useful for a lot of signatures about stars and high energy phenomena, aspects of very hot gas in the universe. And so there's a lot of interest in that, and that would be another area where Habitable Worlds Observatory would also look for more development in general astrophysics, and that also with the extremely large telescope, lots of different science people are looking forward to do with that. Yeah. So on the one hand, I think the search for life cases are really clear as a nice, this is a question we have, and we all want to answer it, and it's also recognizing that most of these facilities, astronomers will figure out how to use multiple ways for lots of different kinds of questions.
Fantastic. Question to Sarah from David here. Can we apply the techniques you spoke of in your work to detect possible life in our solar system? Could we detect subterranean life on, say, the moons of Jupiter or Saturn?
Yeah, so I mean, great question, David. I have bets on the table with people of where we'll detect life first and in what year. Will it be on an exoplanet or will it be in our solar system? I think we will most likely be able to really confirm life in our solar system because you can actually get a much clearer answer. You know, you could go with a probe and, I don't know, a microscope and see little squiggly, you know, amoeba or something. That is possible, where that's not possible on an exoplanet. They are different detection techniques. So in the icy moons of Jupiter and Saturn, like Enceladus, Europa, or more weird biospheres like what could exist on Titan, or there's, you know, the very hypothetical habitable environment in the clouds of Venus, which, you know, I'm a lot more skeptical of. These are all questions that we can answer by actually visiting these planets. Doesn't mean it's not hard. You know, like when we talk about Europa, that's under a 3 to 30 kilometer thick ice layer. How do we go down to that water and get the data back out? You know, do we look for areas of cracks where that water's coming up to the surface? Would we still be able to see life in that? Enceladus, it has these plumes, same on Europa, but especially on Enceladus, these plumes of water. Could we just like capture that and see if there's any sort of microbes that are being ejected? But that water system on Enceladus is not stable for billions of years, so Europa is kind of better. There's, you know, it's going to be involved with missions going there. We haven't been able to see life on these despite having orbiters and missions that are like right there looking at them. So it's not the case of looking for spectra. it will be needing to look with probes. And this is also why these environments are utterly useless to us as examples for exoplanets life. A lot of people are like, yeah, but life could exist, anywhere in the solar system. So why are we focused on the habitable zone, this narrow region where liquid water could exist on the surface? And really, it's because from light years away, we need to look for something with a global biosphere like Earth. If we can't tell if Mars or Europa or Enceladus has life, and we've sent rovers to Mars and we have sent orbiters to Enceladus and Europa and whatnot, then we're not going to be able to find that in an exoplanet analog. So that's a great question. Thank you for that, David.
Brilliant. Now we have one from Eric that's I put in the chat. Very interesting because it's a question that looks at the international aspects, also the political aspect of science we brought up earlier. Is it fair to expect countries with smaller GDPs and fewer people to contribute the same to your field? If smaller countries contribute the 0.4% to 0.5% of their GDP, like US, isn't that fair and equal?
Yeah, no, I think it's a great question. I think there's a number of aspects of this, though, that I'd also like to highlight. So space is kind of, tolerably useless in some ways. We're not curing cancer. We're not like providing education for people who can't otherwise have it. Yet the return to the economy is quite strong. So it ranges between, $3 to $7 for every dollar invested in NASA returns directly back to the US economy and grows the US economy. So I would say in some aspect, you don't need to, it's not an either or. By investing in science and technology and engineering and space research, you are getting money back to your system in a way that helps your country. So I think it's both true that I don't think we should ever spend the majority of our budgets on space research. We should spend the majority of our budgets in things that are making people's lives better, health systems, et cetera. Yet, we should spend some portion of our budget in doing something really cool that we couldn't do on just from like smaller collaborations. So I see it as both of course, every country will have to look at their funding priorities, but you can also see how much it comes back into the system. So I think it's a good reason for advocating for science funding in the space sector.
Yeah, and I'll just add that I think that this is a place where the smaller countries can leverage what they're doing. It's true, it wouldn't be the same absolute investment, but in collaboration with other larger countries, larger entities like the European Space Agency, then there's the possibility to participate. And in fact, typically with this kind of astronomy and planetary science data, it does become open to that global community of researchers. And so everyone really does have a chance to work with it.
Also, just a clarification in Eric's comment, we're not funding at 0.5% of our GDP. We're funding at 0.5% of our tax dollars. Very different number.
I think we
Much
have.
less.
Oh,
Much less.
we have one. I think we have time for our one final question. So this is for both of you, from Martin, and touched on an area I think that a lot of people are into the moment, the probably aspect of our technological advancement that is feeding into all areas of academia. It seems that astronomy research involves enormous commitment in human resources. So how will AI help in accelerating your researches?
Yeah, I'll start. I mean, I think there's incredible opportunity with AI, and often it's specifically in the machine learning context that that we get to use it. That some of these formal approaches of you train the machine on one set of data that you know about, and you know what's there, and then you can test it on further kinds of observations. And so I think a lot of these astronomical questions lend themselves to that kind of approach. There's also the very fact that we are getting to the point of dealing with large amounts of data. So it's no longer an astronomer sifting through a single image, a single spectrum, and looking at it in intense detail. It's suddenly dealing with tens of thousands of galaxies all at once. What are the general properties here? What are the things that we can systematically learn about them? And so that's where some of these approaches are already being employed and will be even more useful. Especially, we have a number of really big data missions, sort of generating petabytes of data. So the European Space Agency's Euclid mission is operating, and we have great data sets from that already. The Nancy Grace Roman telescope from NASA will also be surveying the sky and collecting essentially making big maps of the sky. And then on the ground, the Vera Rubin Observatory, again in Chile. Chile is a really good place to do astronomy from the ground in the Southern Hemisphere. That they think of making a movie of the sky every 3 nights because they'll be looking for things changing. And again, just large quantities of data to sift through. And so we'll have to rely on these kinds of numerical techniques to find what's there.
Yeah, and I think like in addition to just being able to process more data, which we definitely need help with, there's just so much data that we're unable to process. I don't know if you guys have heard of maybe SETI at home or like the LHC at home. Compute power is something that's necessary, and AI is definitely going to help with that. I think it'll just allow us to do a lot more faster, like more research faster, from both the scales of these processing large data, being able to handle that capacity. And also sometimes simulations take, I don't know, 3 months on a computer. And if you can get 3 months down to a couple days or something like that, then that can accelerate the timeline for getting results. So I think that will help from a day-to-day perspective for me. It's great with coding, so you can ask it to, if you have an error in your code, you can be like, can you help me solve this error? What I worry is that our next generation of students is not going to learn how to do the fundamental basics first in order to know how to use AI most effectively and how to tell when it's wrong, because it's wrong a lot. And maybe at some point it won't be wrong a lot, but we've added a lot more data and we're not getting past that sort of, it's still hallucinating 30% of the time. Maybe that'll change, but like there is still this issue. So one thing I struggle about as a professor now is how do I have my students learn how to use it properly? How do they still learn the tools, the mathematical reasoning, the coding reasoning, the physical intuition that they need in order to know when it's lying to them? And you've all seen examples, I'm sure, of ChatGPT being able to basically solve most homeworks. Yet I find mostly my students who use it still fail my course at the same rate as if they weren't using it. So, it's an interesting time for sure. I would say I'm very optimistic about AI on the 5 to 10 year timeline, and I'm a little terrified and combined to some conspiracy theories of a robot apocalypse on like the 15-year timeline. So we'll see, it's going to be an interesting time for sure.
I think on that note of, well, a mixture of hope and also hopefully to ward off the robot apocalypse, I'll join us as we have at the college chapel clock is striking just as I speak. So first, thank you so much, both Nancy and Sarah, for the fascinating conversation. Really, really wonderful to bring it to, well, those who are specialists or indeed non-specialists like myself. Thank you so much. Also for giving up your lunch break, because of course it is over on the other side of the pond. And thank you everyone for joining here your January evening with us. I can give you an official, not yet released little secret. We do have another Zoom event scheduled. It will be in March, 30th of March, looking at the college's Welsh manuscripts. So I do hope those of you who like to join us on Zoom will be able to join us for that. More details in the coming weeks. And we continue our celebrations of the 50th anniversary of coeducation. That'll be Friday the 7th of March in college. We have a preview of a brand new film with some of our first female alumni talking, as well as a brand new photographic exhibition, which is permanently going to be in college. And we invite you to come and have a first sneak peek of that on the 7th of March. But without further ado, thank you once again to Nancy and Sarah. Thank you all for joining. And yeah, we hope to see you once again soon. Thank you so much.
Bye. Absolute pleasure.